So, now we will discuss continuous random variables. We have already completed the discrete random variable part, and we have discussed already some of the numerical examples. Hope you have understood, or you can go through some more numerical examples also. Now, we will discuss the next part. It is called continuous random variable. So, how continuous random variable it will be defined? So, discrete case you can remember that this distribution function is not continuous. So, whenever this random variable, discrete random variable we discussed, it will taking the range of the random variable is either finite or it will be countably infinite. Here this range, it will not take the random variable, it will not take the discrete values, it will take some intervals. So, it will take uncountably many points. So, there are many examples we discussed. Suppose you are throwing a dart. So, like this, some target is there, and now you are trying to throw in the center, but you cannot throw it because we are not that much, we are not specialist. So, we cannot throw always in the center. So, it may fall in some of the places here. So, then we just want to see what is the distance. So, this distance, it may be measured like in a real line, it is 0 to some, suppose this is the disc, and this disc maximum radius is r. So, we assume that at least we are throwing inside the disc, somewhere in the disc. So, then this maximum distance will be r, and it will be somewhere in the distance will be any real number, it will not be a discrete values. So, here we cannot just say that this random variable is just taking a discrete values. In that case, we will consider this random variable as a continuous case. But how we will define this random variable? So, this discrete continuous random variable defined as follows. You can see this. Let x be a random variable with cumulative distribution function f x x if f x x is continuous and also has a derivative which exists everywhere except at possible a finite number of points, and it is piecewise continuous, then x is called a continuous random variable. So, we will discuss all these things. So, in that case, so what it is saying, so this f x x, this cumulative distribution function, this will be, this is nothing but it is the definition of a cumulative distribution function for x belongs to real number. It is not only continuous, its derivative exists, and this derivative also continuous, derivative is continuous except finite number of points. So, we say that it is a piecewise continuous. So, and is piecewise continuous. Piecewise continuous. So, what is piecewise continuous? So, you know that graphically if we represent a continuous function, so it should like it is not anywhere it is not broken in this function. So, graphically we represent as a continuous function. So, there is some specific definition of continuous function, you know that some epsilon delta definition. So, like for any epsilon greater than 0, there exists a delta greater than 0, such that f x, this distance will be, suppose we are saying that f x is continuous at a point epsilon, at a point x naught, it is continuous. So, that if you take a domain x naught minus delta, x naught plus delta, then this function also will be inside the interval f x naught plus epsilon, f x naught plus epsilon. So, if x minus x naught is less than delta, then this should be, then it is called a continuous function. It is equivalent to show this graph. But what is piecewise continuous? Piecewise continuous means, suppose if you are representing a function, any function, suppose g, it is from R to R. So, then this function will be called piecewise continuous. It may not be continuous over R, but you can break the whole interval into finite number of intervals. Suppose it is minus infinity to some point a, and then a to some, suppose a1, some a1 to a2, like this, some a1 to a3, like this, some finite number of interval, and then a to infinity, such that in this it is continuous inside this interval. Then there may be a discontinuity, then it is continuous up to a2, and then there may be a discontinuity. So, it is continuous up to a1. So, suppose it is like this. So, then this is like this. So, basically what we are showing, that it may be discontinuous in a finite number of point, but it is continuous. If you break whole this interval, then it is continuous in that interval. So, finite number of interval you can break in the whole R. So, then this is called a piecewise continuous. So, whenever if you find the distribution function, it is continuous and difference derivative exists, and derivative also they exist for all x in the real line, and also derivative is piecewise continuous. So, then this random variable, it is called a continuous random variable. So, continuous random variable, this distribution function. So, if you little advance, if we discuss it, so distribution function will be absolute continuous. We are not going more details about it. So, it means that there will be a function f, small f, in the R to R. So, there is a function R to R, such that this distribution function f of x can be written as, this is nothing but probably that x less than equal to x, can be written as minus infinity to x f x t dt. So, this there will be a function. So, this function is this f. So, then this f x is called absolute continuous, and also this with respect to this measure we say Lebesgue measure. So, we just here, so then f x will be absolute continuous, but if you do not go in that direction, this is we not required. So, we will assume that f x is a distribution function which derivative exists and is piecewise continuous, and whenever its derivative exists, then we define this derivative is nothing but f x x by f x x, but this is nothing but derivative of this function, because for continuous random variable we say that the derivative exists for all x. So, then for all x belongs to real number. So, then this function, it is some special name, it is called the probability density function, probability, so density function, probability density function. So, you may understand that it is will understand it is this probability density function is analogous to the probability mass function in case of discrete case. In discrete case, this derivative does not exist for this distribution function, and we define probability mass function. But in the continuous case, a derivative exists for all x. So, we define here the probability density function. So, probability density function, it will be in the context of continuous random variable, and probability mass function, it will be in the context of probability mass function will be in the context of whenever x is a discrete random variable. Now, what are the properties of the probability density function? So, you can remember that we have already discussed some of the property in the case of probability mass function. These are the properties, that it will be always 0 to 1, it will be equal to 0 if it does not belongs to the range of this random variables, and it is sum of these things will be 1. So, now and also how we can get this distribution function from the probability mass function. Here also we will discuss these similar concepts. So, the probability function, it is defined. So, a probability density function is defined by, so by the function f of x is equal to derivative with respect to the cumulative distribution function f x x. Now, what are the properties of the probability density function? So, one property is that, so because it is derivative of a non decreasing function, f x x is f x x, we have already discussed that the what are the properties of the cumulative distribution function, because cumulative distribution function always non decreasing. So, you can remember that cumulative distribution function, we have proved this also. So, here you can see here we have discussed. So, if x1 is less than x2, then f of x1 is less than equal to f of x2. So, here we have already proved that this is non decreasing function. So, cumulative distribution function is non decreasing function. So, this probability density function, it is the derivative of the CDF f of x, this will be always greater than equal to 0, for all x belongs to the real number. Second is that probability mass function, sum of all the possible value it is taking. So, here because it is a continuous random variable, it will be sum will be replaced by integration. So, this is minus infinity to plus infinity f of x dx, this is the probability will be probability of the certain event, this is nothing but is equal to 1. So, that, and also third is that, so how we will find, because in this case the probability we will talk about this random variable taking in an interval. It is not a particular point, it is not discrete point it is taking, it is a continuous random variable, it is taking some intervals. So, we can discuss what is the probability that a is x is belongs to between a to b. So, it is nothing but same as to say that x belongs to some you can okay. So, as you are writing this as a open half, so closed. So, a b, where a b two real number, where a and b are two real number and a is less than b we are considering here. So, you can think less than equal to b, because here only one have open. So, a is less than b. So, then in that case, so what will be the probability that, how we will find that using the probability density function? This is nothing but a to b, integration a to b f x x dx. So, what is the graphical interpretation of the probability density function whenever x is a continuous random variable? So, in that case, so suppose your density function looks like, suppose f x, if I draw f x x, so we will show some of the example, then it will be more clear. Just we are writing just a property. Suppose this is a density function. So, suppose this is a and this is b, and we want to find the probability inside this interval x is taking the random variable taking the value. What is the probability that the random variable x is taking inside this interval? This probability is nothing but, so if you take the area under this curve, so this is nothing but, this is the probability that x is greater than a less than equal to b, which is nothing but a to b f x x dx. So, this is the probability. Now, if you because this is, so if you take this is as this also, suppose x greater than equal to a. So, in that case also this probability will be same, because under this curve this is, it does not change, a to b f x x dx. So, you can take closed interval, half closed, half open interval also. So, in the continuous case, one important property is that probability at a point, any point, probability at a point, some small x, suppose if you say any real number, suppose 2, this is equal to 0. So, if you take suppose a at a point a, this is equal to 0. So, where a is any real number, probability at a point is 0. So, this is the difference with the discrete random variable and continuous random variable. For discrete random variable, x taking some of the discrete points and probability exists on that non-zero probability exists on that discrete point only. But for the continuous random variable case, at a point the probability is 0. So, because if you can think like what is x equal to a. So, here you can see that probability that a less than equal to x less than equal to again a, if you consider this is nothing but a to a f x x dx. So, this is nothing but 0, because on a line only you are not taking any this distance anything here. So, in that case on a line in a 2-dimensional space the area is 0. So, in that case it is just a, it is not a proof that at x equal to a it is 0, but it is just a intuition to understand it why it will be 0. So, because the probability you are finding by under the curve, area under the curve. So, when we are trying to find area under the curve when there is no 2 points, only 2 points are same, it is just A becoming B going to close to A. In that case, its area goes to 0. So, it is one example that suppose someone ask that is the always true that probability or impossible event means that it is a null set only, impossible means it is probability maybe 0. So, impossible event means it cannot happen, but in that case here you can see that this if you are considering a continuous random variable, some of the real number it is possible, it can come, it is not an impossible event, but the probability is 0. So, even if you take a countable set also, the probability on a countable set it will be 0, because because by the this axiom 3, if you consider this collection of countable set like this, then probability at x is equal to ai at a point it is 0. Now, what will be the probability, suppose A is this set, so then what will be the probability of A? So, by it is nothing but the countable union of I is equal to 1 to n this ai. So, this is nothing but probability of this. So, this probability of this is nothing but by axiom 3, this is nothing but summation of I is equal to 1 to n probability that x is equal to ai. So, that x is equal to ai is 0. So, that is why this is nothing but because sorry n is equal to 1 to infinity. So, this is nothing but this is I is equal to 1 to sorry not n, this is infinity. So, this is I is equal to 1 to infinity, because all probabilities are 0, it is a convergent series and it will converges to 0 only. So, these are the some of the properties. Now, how you will suppose you have given cumulative distribution function, you know the cumulative distribution function. So, somewhere it is given. So, then how you will find the probability density function? It is very straightforward, because it is defined by the derivative of this ddx of fxx. So, this is the definition of a probability density function. So, this is ddx of fxx for all x belongs to real number. Now, suppose somehow you know first the probability density function, or somebody gave us the probability density function, this is the form. So, we will discuss some of the in the continuous random variable cases, mostly it will be convenient to understand it by density function, probability density function. Most of the time we will discuss the example by density function. Whenever density function is given, how we will find the cumulative distribution function. So, what is cumulative distribution function? So, cumulative distribution function is nothing but probability that x is taking less than equal to x. So, that is nothing but so probability x equal to less than equal to x is nothing but here actually this is same as x less than equal to x, this left hand side we do not write, it is nothing but minus mu to plus x is taking the in the interval. So, we know that whenever we are talking about whenever a less than x less than equal to b, so then this in probability is nothing but fxx dx. Now, if a goes to minus infinity, so we can find this probability here. So, this is the in general case. Now, here, so we know that probability that what is a less than x less than equal to b, this is nothing but integration a to b fxx dx. So, this concept if you take a goes to minus infinity, so then this probability we will find minus infinity to x fx. So, here we are using this variable x here, fix some real number. So, what we will do here, we will the integration we will take some other variable dt. So, here also we will take dt. So, a to b fxt dt. So, that means this is the density function, suppose this is the probability density function, and then the basically a to b we have already discussed, but it is actually this x is a real number. So, then what is the area? So, this is the actually area minus mu to x, and this area is nothing but fxx. So, this is nothing but this value minus mu to x fxt dt. So, this is the cumulative distribution function with respect to the probability density function whenever this probability density function are given to us. So, let us discuss some example of continuous random variable or probability density function. So, this example, suppose let us consider let fx. So, first we will check whether, so suppose f(x) be a function defined by, so f(x) is a function defined by, so suppose this is equal to, suppose x square, sub c into x square, some constant, whenever x is greater than -1 less than less than suppose 3, suppose let us consider. So, and 0 otherwise, 0 otherwise. Suppose let us consider this. So, c is a constant where c is a, we have to find that value. So, question is that find c so that f(x) is a probability density function. Probability density function of a random variable x. So, we need to find the c. So, first of all we have to check that whether for any c it will be always a probability density function. Then question that whenever you are finding the c, find probability that x is taking suppose less than or equal to 0. Okay. So, let us take find the value x less than or equal to 0, probability that x less than or equal to 0. So, this is the question suppose. Now, how we will find that? So, because it is a probability density function, because it is asked that c is a constant, find c so that f(x) is a probability density function. So, because it is a probability density function, it will satisfy the condition of the probability density function. These conditions are written here. f(x) will be greater than or equal to 0, minus infinity to plus infinity f(x) dx is equal to 1. f(x) is piecewise continuous because the derivative is piecewise continuous, and this is assumption of the continuous random variable. A to b f(x) this probability can be written in this way. These are the some of the properties. So, now we have to check that all the properties are satisfied or not for any values of c. First of all, you can see that this f(x) will be greater than or equal to 0 whenever c is positive, because it is x square, c is positive. Then f(x) is greater than or equal to 0. f(x) is greater than or equal to 0 if c is positive. Now, second property is that this, if you take the integration minus infinity to plus infinity f(x) dx, this should be is equal to 1. Now, if you do the integration, because you can see that this is non-zero only in this interval possibly, otherwise it is 0. So, that is why we will take this, you will divide this whole interval in this way, which implies this is minus infinity to minus 1 f(x), this is f(x) dx, f(x) dx plus minus 1 to 3 f(x) dx plus then 3 to infinity f(x) dx, this is equal to 1. So, because f(x) is 0 in this interval, so this will be 0 only, and this is minus 1 to 3 c x square dx plus again 3 to infinity if f(x) is 0, so this will be equal to 0. So, then so this is equal to 1, we have to solve. So, then we have to do this integration. So, what is the integration? So, which implies minus 1 to 3 c into let us see that integration. So, this is c into x square. So, integration of x square is x cube by 3. So, then this is x cube by 3 and the limit is minus 1 to 3. This is minus 1 to 3 and then this is equal to 1. So, which implies x cube, this is c by 3 x cube 27 minus of x cube, again it is coming minus 1. So, this will be plus 1. So, please check that. So, 3 into 27, then minus of minus 1 whole cube. So, again another minus is coming. So, this is equal to 1. So, which implies this is C is equal to 3 by 28. 3. So, that is why our density function it is coming f x is nothing but 3 by 28, this is x square whenever x is greater than minus 1 less than 3, this is equal to 0 otherwise. Okay. So, note that again I am mentioning here. So, this function whenever you are defining, if you take it is a open interval or you can take half closed, anywhere you can keep closed or open, it does not change because it is a continuous random variable. At a point the probability is 0, so your probability will not change. So, you can either represent it by this closed interval or half closed, half open interval, right side closed, left side open, or left side closed, right side open, or you can represent by open intervals. So, it will be same. So, now next question is that, so you can see that this function satisfy all this relationship, all the properties, mostly these are the important properties. F x should be greater than equal to 0 and integration if you take it will be 1. So, we have this constant 3 by 28, then it will be 1. Now, if you find the, how you can find the probability that x is less than equal to 0. So, probability that x is, so the second question was that what will be the find probability of x less than equal to 0. So, x is less than equal to 0, this will be nothing but, so integration minus infinity to, so basically x is less than equal to 0. So, left hand side there is no, it is not given any bound, that means we consider it is greater than minus infinity. So, to 0, then this is f x dx. So, now this density function exists non-zero, it will be whenever it is greater than minus 1. So, we will break this interval. So, minus infinity to minus 1 f x dx plus this is minus 1 to 0, minus 1 to 0 f x dx. So, then what we will find? So, this will be nothing but minus infinity to minus 1 f x dx. So, because this is 0 in this interval, so this will be nothing but 0 plus minus 1 to 0 f x dx. Minus 1 to 0 f x dx is minus 1 to 0 f x is here. So, this is minus 1 to 0 3 by 28 x square dx. So, then what we will do? We will do the integration, this is nothing but 3 by 28 x cube by 3 minus 1 to 0. So, then it will be nothing but which is equal to, since it is 0, it is 0 minus of minus 1 whole to the power cube, it will be minus 1 again minus. So, it will be plus 1. So, 1 by 3. So, it is 3 by 28 into 1 by 3. So, this is cancelled. So, this probability is nothing but 1 by 28. So, this is one example of probability density function. We will discuss some more example. Suppose let us consider another example here.